So again, thank you very much, Luca. It's very nice to be back again. And I will talk about a piece of research that was initiated about 5-6 years ago. And since then, many people were involved in this research, of which the list is given here. And the credit goes to these people who did most of the work, and I was observing from some distance. So this is the actual work that I'm presenting today. It started off with testing a practical piece of software, and now my mouse stopped working, but that's not a big issue. I can use this mouse here. I just tried. Yeah, now it works. It started off by testing an actual piece of software developed in the company for bank transactions. I will explain the context, and then I will explain a little bit of the technical issues that were involved in testing that piece of software. And I will then move to theory and present some slides on the theoretical background of the tool we use for model-based testing of this software. Then we move back into practice and show you some results from application of this theory to this piece of software and what kind of problems we observed after we tested the system. So from that we distilled some theoretical problems. So we observed that there are some shortcomings in the theory. So we went back to theory and worked out some new pieces of theory that's slightly more recent. So the last 2-3 years we've been developing theory about model-based testing. So I'll explain, if time allows, 2 of these recent theoretical developments. And well, now I've just started a new group, and we will start implementing these things in practice and measuring things. So I don't have any concrete results, but I will tell you about the new challenges that are ahead of us in implementing all these pieces of theory and applying it to practical cases. And let's keep this interactive, so at any moment of time, if you have questions, please do stop me, and then we can change the course of the presentation a little bit depending on the questions. Okay? So, as I said, it started off with a piece of software which is called funds transfer switch. And this is basically a router which sits in between point of sale terminals, ATM machines, teller machines, and web services, banking services, on one side, and on the other side, the core banking of a certain bank. Right? And what it does, it receives transactions from all these terminals, and depending on the target bank, either it routes it to the local core banking system, or it routes it to the interbank network, and then eventually it should receive the response from one of the 2 sides and route it back to the appropriate terminal. Right? So it's a simple router, relatively simple router, which does routing of these transactions. And the particular system that we were looking at was an operational EFT switch which was shipped to one bank at that time and later on to a couple of more banks. It was about 100 kilo line of Java code. It was an embedded device that you could mount on a rack, and then you connected it to the network, and it would start doing these routing things for you. And, well, it was a rather complex piece of software, so it used lots of acronyms that I didn't know about and I still do not know about. So it's a rather complex architecture that on top of which this piece of software is built. And it was tested using normal scripts that you would do for, say, Java unit testing, JUnit type of things. But as I will show you, there are lots of complications involved that were not properly covered by the manual tests. So they were asking for a more structured view of testing and whether we could help them with some more discipline testing. Yeah. So we said, okay, we will look at a very simple part of the software, basically the main router that does this routing of transactions back and forth. But the problem was that the view to this domain logic was very much obscured by lots of other components that sit around this domain logic. So there was security, logging, lots of other things happening around this domain logic. And accessing this from the outside world, if you want to have a black box view, is not very easy. So you need to abstract from a lot of things in order to project the behavior on the main thing that you're interested in. And moreover, this was not a single-threaded application. Naturally, it had to be parallel. So So there are lots of things happening in parallel, and that even made testing much more difficult. So coming from, say, process algebra background, I thought we can make use of some of the theory that we have been learning for many years, and make models of this behavior and try to use those models in order to turn this ad hoc way of testing into a more disciplined practice. So here is a typical application of EFT switch. What it does, it receives, for example, a purchase request from a point of sales terminal, and then it forwards this request to the core banking system. It receives the response, and then it forwards the response to the post terminal. Very simple, but unfortunately things can go wrong. For example, the user may first send a purchase request, but after some time he or she may decide that now I want to reverse this transaction. So it may send a reversal request, but in the meanwhile, the EFT switch might have sent already the response, the request to the core banking and received the response, and even have forwarded the response to the point of sale terminal. So by this time, it's kind of too late to reverse the transaction to the core banking. And the protocol specified by an ISO standard that we will present next specifies that you should immediately reverse, so acknowledge the reversal to the point of sale terminal, and then later settle this with the core banking system, right? And there are lots of these type of scenarios that can go wrong due to asynchrony and delays and concurrency. So there is this ISO standard 8583, which specifies all sorts of details for card-based transactions, down to the detail of the size of the packets, all the bits that you have to set in these packets, even the size of the plastic card that you use for say, credit cards, what kind of magnet strip you should put on that, etc., etc. But what is interesting for us is that it does specify some of these scenarios in some detail, and it also has a kind of high-level description of how these scenarios are combined. So you first do an authentication, and then you can do a financial transaction, and then there might be a reversal, and they should be combined in a certain order. Okay. So, and then on top of this, we have the practical test cases, the practical scenarios that we call business rules, how these things can be combined, and what kind of data items should be attached to these messages in order to perform a certain transaction. Okay. So we took all of this, all of these specified aspects that are taken from this ISO standard, and we said we make a kind of neutral model that reflects what the standard says, and we'll use that in order to test the EFT switch. Right, so that was the idea. The problem is that there is not a single terminal that interacts with the switch, but there are also concurrent instances, and we had to take care of that as well. So many of the interesting bugs that are very difficult to find and very difficult to trace emerge from these type of scenarios that you run a number of these transactions in parallel, and then the interleaving may cause very pathological interleaving of messages, and that can cause serious problems. So we also had to take care of parallelism that is inherent to this type of application. If there are any questions, please do stop me. I do not want to go too quickly over this. So what we said we will make a model based on the ISO standard, and then we will use the theory of model-based testing, which I will present next. And the theory will help us generate the test cases automatically. So once we have this model in place, then there is very little effort generating test cases from it. And then we can also log and prioritize test cases for things like regression testing, so that if the system changes, you can test again whether the old behavior, the old good behavior is preserved and bad behavior is fixed. You can measure test coverage, and you can also test these interesting scenarios by running particular, say, sequences in your model. Okay, so that was the idea. And what is essential is, of course, the first word in this three-word sequence, namely model. So we first had to build a model, and this is a very non-trivial thing. So one of the main obstacles of applying model-based testing is that models do not exist in practice. So a typical piece of software usually has some vague description in some UML say, notation, and this is made at some stage and never updated later, so these models are usually useless. And making models is a rather costly business. If time allows, I'll get back to this issue of making models. But in this case, we made the model ourselves. So there were a group of, I think, 3 people who started making models out of this ISO standard. And model is nothing but an abstraction from reality. Well, in one presentation, I put female models, and then there was some complaint by discriminating, so now I put male models. That's also possible, yeah. But anyway, so these are abstractions from reality. They do not present the whole reality because the whole reality is too complex to capture. And they separate different concerns. So if you have the domain logic, the model allows you to focus on the interface behavior of the domain logic and abstract from all these other things that happen in the environment. And moreover, you not only can specify the behavior of the system, but also can simplify the behavior of the environment by the model. So you can say, I'm only interested in these type of sequences that happen in the environment. Otherwise, the environment is so wild that you can never cover all possible interactions, right? So model serves 2 purposes. First, specifying the desired behavior, and also confine the behavior of the environment, because the environment by itself is too wild. All possible interleavings are impossible to cover. Right, so what we did, we went back to the theory of concurrency, and we looked what is there. So I will start.
Sorry, Mohammed.
Sure.
So, also, did you consider actually learning the model?
That's very interesting.
The approach with this number.
Yes. This is a very recent development, so by that time I don't think Fritz had done that. But there's a recent trend in this whole field. It's called test-based modeling, because models do not exist. What you try to do is that you try to interact with an existing system and abstract from the behavior a model that you can use later for testing. Right? So test-based modeling. You try to test the system, test an actual system, and from your observation you try to construct a model that you can use later for testing. Of course, the caveat here is that you are building models from a system that by itself may contain faults, right? So your model then reflects also those faults. But of course, that's better than nothing, because you can show these models to a domain expert and say, is this the behavior that you expect from the system? This is better than modeling from scratch. And you can also do all sorts of things. So compare 2 different running systems and then take difference. But this is a recent development that some people have started, and by that time it didn't exist, and I think that's a promising way. You didn't try that. You haven't tried that yet, also in this case. Is the question and answer clear to everyone in the audience? So absence of model is an essential problem in this domain, and one way to solve this is to learn models from operating system, operating a functioning system. Right, so as I said, what we can do, we can capture the behavior of the system and the environment in terms of models, and the type of models that we will be looking at are these type of automata-like models, finite state machine-like models, in which you specify, for example, that the system may receive from a point of sale a request, purchase request, and the question mark here denotes receiving the message. And as a result, you may have a choice. This is a very pathological model, so I do not claim this is an actual behavior, but as a result, you can send to core the same request, so forward the request to core, or you may time out, so you may receive from the clock, say, a timeout message. As a result, either way, if you receive a timeout, you will go back and repeat sending the request to core, or if you do not time out, you will receive the response from the core, and then you forward it to the point of sale. Right? This is a typical model that we consider. Question mark is receiving a message by the system, and exclamation mark is sending a message from the system to the data. Right? Now, the idea is that you take this model, you generate test cases, you feed them to the system, and by observing what the system spits out, you can conclude whether the system is implemented correctly or not. So you take the system as a black box, you do not have access to what is hidden, the final state machine that is hidden in this system, but by feeding inputs to the system and observing outputs, you can conclude whether the system implements an equivalent final state machine or not. Right? That's the basic idea of model-based testing. Now, how can we build such a theory. So how can we build a theory that allows us to conclude that a system is implemented correctly or not? Of course, we can take this black box and open a hole in this black box by which we can observe something from the system. And the simplest thing that you can do is to put a button here that allows you to take one possible next action and then observe whether this possible next action coincides with what you expect according to the model. Right? So, for example, you can test this black box against this model and press the next button. If it shows an A, then that's fine. If it shows anything else, you conclude that the system is incorrect. And then you press the next button again. If it shows B, then that's fine. If it shows anything else, then that's, again, incorrect. And then you press the next button, and if it shows anything, then that's incorrect. But if it does not show anything, it means that it has come to a quiescent state. It has come to a rest state. And that's the correct implementation, because here you should come to a rest state. Right? Is this clear? So if you use this notion of testing, this notion of observation, then you come to a notion that is called in the literature completed trace equivalence. So you compare the specification with the implementation with respect to the possible actions that the system can take, and also you can observe when the system has come to this quiescent state, when it has come to a rest state that cannot do anything further. But the problem with this is that it equates, it identifies too many systems. Cannot distinguish sufficiently. For example, this is a typical example from the concurrency theory literature. These two systems are considered equivalent according to the notion of completed traces, because the completed trace of this one is A, B, and then quiescent. Right? A, C, quiescent, and the same for this side. Right? While these two systems are very different. A typical example to explain this is this example of tiger on one side and prince or princess on the other side, right? So this is a door, and then by opening the door, you are confronted with two choices. Either you can live with a prince or prince of, say, the prince of your, say, dreams, right? So you can live happily forever, or you can be eaten up by a tiger. And of course, in such a case, if you're confronted with such a choice, you will make the right choice, right? So you will just go the right way, and then you will live happily forever, right? But this is a very horrible system, because you're confronted with two doors, and then if you happen to take the wrong door, then you're doomed, because if you take this door, then you will be eaten up by the tiger, and you have no choice, right? In practical systems, this is a much worse implementation than this one, because this can lead to lots of deadlocks. Think of this as a coffee machine that can eat up a coin and then produce either coffee or tea. So after you put your coin, you have these two lights lit, which allow you to choose between coffee or tea, right? And, well, no matter what you choose, in this system, you always get your option. While here, you put a coin, and then the system by itself decides whether you will receive a coffee or you will receive a tea, for example. And in 50% of the cases, if this is a fair choice, you will want something that is not provided by the system, right? So this shows that completed trace equivalence is not the right notion to test actual systems. Is that clear? Right? Any questions? Anything unclear here? No? Okay. So another thing that you can do, you can control the system a little bit more by putting some knobs here and then determining what you want the system to do for you. So you can say, I want you to do something by pressing the next button, but this something has to be either B or C. In this case, it should be only an A. And then you can, of course, change the knob and then do the same experiment by requiring the system to do B or C, right? And in this case, for example, if you put the knob in such a case that you can only do an A, it will, of course, do an A, but you can then tell the system, I want only a B from you. And then in some cases, if you run this experiment, you will see that the system is not able to do the B for you. So it will come to a quiescent state, because the only thing that it can do, according to you, is B, but since it has taken the wrong door, it will not be able to do this B for you. Right? So this allows us to observe a little bit more from the systems. And this is, for example, you can also distinguish these systems. I think I should skip. And this is the notion that has been developed by people like Rocco De Nicola and Matthew Hennessy, and it was called testing equivalence, which is a rather powerful notion. So it allows you to compare systems by controlling the type of observations that you expect at each state. Right. I think I'll skip some of the details. You can, again, strengthen your power of testing by adding more observations. For example, you can add a light here, which, depending on the configuration of these knobs, can tell you whether the system can possibly do something or not. Right? So here, you tell the system, I want to do an A. It can always do an A for you in the initial state. So it will do an A and go to a state. And then depending on how you put these knobs, this light may turn on or off. So if you put only A and B as the possible actions, since here there is no A or B possible, then you see that this possibility is not included in the possible futures of the system, right? So then you know that you should change the knob and do something else by which the light will turn off, and then it will take one of the actions that you specify. So this will be a new notion of testing that also exists in the literature. So you can play with this a little bit around and take an action eventually. But you have observed much more because in the meanwhile, while doing this experiment, you can observe what was possible throughout this experiment of testing. And this is the notion that was developed by Ian Phillips. So I will skip again this. This is called refusal testing, which is a more powerful notion of testing in practice than testing equivalence of De Nicola and Hennessy. And it's a practical notion as soon as you have the possibility of observing timeouts in your system. So if your system is kind of time sensitive and you can wait for a bit and decide, okay, the system is not going to respond at this moment anymore because it has gone beyond its time limit, and then you can continue doing testing, then this is the right notion to choose from. Right? Otherwise, testing equivalence is good enough for you for practical purposes. But anyway, so this is another notion that was developed, I think in 1998 or so by Ian Phillips, and that's also an interesting notion which allows you to observe timeouts and then proceed depending on what you observe before or after time. And there is a whole spectrum of these notions in theory. So this was developed by Rob van Glabeek many years ago, I think 1995 or I don't remember the exact date. But anyway, he developed a whole spectrum relating all these different notions of observation. And the notion of observation that we have just seen is just here. So you can go much higher in the hierarchy of Rob van Glabeek. But the moral of the story is that this is already a rather powerful notion. So there is very little chance that you need any of these more powerful notions in practice for testing. Right? So those notions that are below in Rob van Glabeek's spectrum are sufficient for some practical purposes, but it's very unlikely that you will need any of these more distinguishing notions. Anyway, so this was the theory. So far, this is good for testing, but we need a bit more. Namely, we need to abstract from certain aspects of implementation. Like in this particular example, we had the domain logic, and there was security, logging, all these other things that happen around. And we only want to focus on the domain logic. So the thing that we need, let me go a bit further. The thing that we need is to be able to allow partial specifications of the system and then focus only on that aspect while testing this particular model and then abstract away from all the rest. This has also been done in the literature by Ed Brinksma. He said, if you want to test whether an implementation is correct with respect to specification, then what you should do, you should look at the traces that you observe, but only look at those traces that are specified in this particular specification. And you can neglect the rest for the time being because you're only concerned with this particular aspect, right? So what you do, you observe the possible behavior of the system, but you neglect all those traces that are not included in this current specification. You throw them away, and then you check whether the behavior that you've observed so far is included in the traces of the specification. That is specified by the specification, is included in the traces of the specification itself or not. So this way you can do, say, this partial testing of different aspects separately. So you look at each aspect once, you test that completely, and then once you establish that this aspect is implemented correctly, you go to the next aspect. Right? One more addition, and then I will be done with the theory so far, is that you need to distinguish between input and output. In practical systems, you usually call a method and then you expect some output from that method. You usually send a message and you expect some response from your system, right? So the theory should also cater for this difference between input and output. This is the system as it should behave, so it should receive a request and then it should produce a response or error, and this is the test case, so it should send a request to the system and then observe a response, for example. And this also has been done in theory, so there is this theory of input-output conformance testing, which allows you to distinguish between input and output by combining refusal pre-order with this distinction between these two different types of actions. And this is called IOCO in the literature due to Jan Tretmans. So this is the theory that we picked as a candidate that could be useful for testing this actual system, this practical system. So what we needed to do, we needed to make a model of the EFT switch, generate test cases using some engine, and then run that on this black box. And we wanted an engine that would allow us to generate test cases with respect to this input-output conformance testing that exists in the literature. And here is an example of a test case. So given this specification that tells the system can receive a B as input, and then either it should produce an A or do something invisible, denoted by a tau, and then go to this state, you can generate this test case, which tells you, okay, initially you may decide to provide B as input to the system. So you produce output B, which will be fed as input to the system. And then you can observe either an A or this is quiescent. This is the action that denotes that you should not observe anything visible. So if you observe A, then this is fine because you have seen a B and then you have taken according to the specification. This transition, you're here. So this is allowed by the specification. Another thing that you can do is that you can receive a B, and then you're here, and then take this invisible action and you're there. There you can observe quiescent. Right? So there you cannot do any visible action. So this is also allowed. So you can observe both an A or quiescent and quiescent after doing this empty B. Okay, here you can decide I want to test more. So I want to observe, for example, more. And if you observe an A after having observed quiescent, then you go to fail state, because after you observe quiescent, you must have been here, and here you cannot do any more action. So if you observe anything, then you can conclude that the system has been implemented incorrectly. While if you continue observing quiescent, then that's okay. Of course, you can expand this further if you want to test more. This is a very simple pathological example, so it doesn't make any sense to go further. But in practice, you have the choice of expanding your test cases as much as you have time. Or as much as you want to cover your specification. That's also possible. But anyway, suppose you have observed an A, then you observe a second A, then you fail because you have been here, and here you should observe quiescent. Right? So if you observe two A's in a row, then you go to the fail state. And if you observe quiescent after an A, then that's fine. So you can test further if you want, or you can say, so far I haven't found any bug. Right? Okay, so I will skip over these. So what we did, so this is the master student who actually did the actual implementation. We made models of the ISO standard. There were 25 time automata models that were represented like this. So this is the smallest time automata represented in the purchase scenario. And the bigger one was, I think, at most twice as big as this one. So not much more complex. And we made the modeling in a tool called UPAL. This is developed in Uppsala and Aalborg. It's a rather user-friendly tool for modeling small systems. And this was small enough to be at least modeled in the form. And then what we have to do, what we did is to build an interface, an adapter that would take these abstract messages, textual messages, turn them into TCP/IP packets that would be understood by the actual system, and vice versa, strip down the TCP/IP packets and feed them as textual messages to the UPAL engine. So the UPAL engine will generate these trees for us, these test cases, but the messages that are mentioned in these trees are too simple to be understood by the system. So you need to write a rather sophisticated piece of software that would allow you to translate these messages back and forth. And this is a non-trivial aspect of mobile-based testing as well. Because oftentimes this gets as complex as the engine for test case generation. You need to know a lot about the model itself and how data is attached to messages. Anyway, so this was a rather complex task, but it was done, and then we could translate messages back and forth between the test case generation engine and the actual system, and what we added was the coverage metrics to the standard coverage metrics, so there was nothing fancy there, by which you could see how much of the component that we were testing was covered by this test campaign.
So an important aspect there is the agnostic trace generation.
Right, so I will show a couple of examples, not in much detail, but a couple of examples of bugs that we found in the actual system. And the interesting thing is that some of these bugs were known, so they knew that the system crashes sometimes, but they didn't know why. And the good thing was that, I will show you later, we logged all these traces, and we could pinpoint when the system really crashed. So that helped them trace this back to a fault in the code. Any other questions? No, okay. So that's what I just said. So we also wrote a small piece of software that would log all these interactions. And you could use some of these as test cases for regression testing later. And you can also observe what has been done in the process of this testing campaign so that you can map those failures to concrete traces of interaction with the system so that you know what went wrong. Yes, yeah, right. Right, true. So here you record the test case, and UPA also spits out this trace for you. That's true. Right. So given the time, I should go a bit more quickly through this. I will skip through all of these. So here are two examples of the bugs that we found. This is a rather long trace. I don't remember how long, but say in the order of hundreds of steps. By which you could find a known failure of the system, and we could find the root cause for it. So that we could find out how can we make the system crash due to a non-pointer reversion. And there were also other mistakes that were found that were say associated with the poor exception handling. But the disappointment was that this had a very poor code coverage. So we only could cover 40% of the statements. So that's the deepest notion of coverage that you could get. And that's not something satisfactory. I can explain a little bit why this code coverage was not as good as we wanted. Basically, the idea is that here you generate all possible behaviors of your system, and then you randomly search throughout this huge space. And if your search is not guided in any way, then you may, first of all, repeat testing the same path a number of times, and you also may miss a lot of important behavior because you just randomly tested in this huge state space. So that was one of the reasons. Another reason is that the tool that we used, so UPAL-Tron was the tool that we used, had very poor treatment of concurrency. So what it tried to do, it tried to compose these concurrent automata with each other and then generate the state space, and from that it would generate test cases. And that's not what you want to do. You want to on the fly generate these trees without generating the whole state space of your system. That's too huge to build for a concurrent system. So these are two reasons why this code coverage is not satisfactory, and we are still working on a good notion of coverage for model-based testing. I believe this is not yet there, so this is one of the shortcomings of this whole theory. Right, so from that we distilled some theoretical problems, and I'm afraid I cannot get into details of these problems given the time. Compositionality is a huge problem. Asynchrony is another problem. I will show you a small example that shows
what can go wrong when you interact with systems asynchronously. And this was a typical asynchronous system because the connection, the interaction was through a network connection. A TCP/IP protocol was in between. Data specification is a huge problem that we are working on, and we still do not have a good answer to it. We believe we will be busy with this. We have been busy with this for about a year, and we are still working on this. And variability and testing different products of a single product line is another interesting problem that we are looking at. So suppose you are developing different variants of the same system. You don't want to test each and every of these variants separately. So you want to have a kind of factor out test case that tests these common features and then only looks at the differences for each product. And that's something that we are still busy with. Now, given the time, I think I should skip through the compositionality and only show you an example of the problem with asynchrony. So, a very favorite example of concurrency theory is coffee machine. I've already used it to show the difference between these two transition systems. I will also show you the problem with asynchrony using this metaphor. Suppose you have a coffee machine, and the test case for the coffee machine is as follows. You can either put a coin inside the machine, so you can either feed money to the machine, or you can observe that the machine has given you money or coffee. So if you observe that the machine gives you money right away, of course you're happy, but it's not a good implementation, right? You lose money, no problem. So that's a failure. And if you get coffee without paying, that's also not correct implementation, right? But suppose you can feed money without observing these two, then you can test further. And then either you, after putting money, you see refund, that's fine. So if after some time you don't use the coffee button, then the machine should refund your money, so that's fine. Or without pressing the coffee button, the machine produces coffee, that's a failure. Or you feed this input to the system by which you press the button for coffee. And then if you press the button for coffee, then if you get coffee, then that's fine. If you get refund, then that's not fine because the system should give you coffee, it should not give you money. And if you don't see anything, that's also wrong. So that's also failure, right? So this is a test case for such a coffee machine. And if you interact using this test case with the coffee machine synchronously, then things go fine. For example, you can put a coin inside the machine, and then you can wait for some time and get your money back. And that's a past run of the test case, right? Or you can put the money inside the machine and then press the button. So this is pressing button. And then you can get your coffee, and that's again a past run, right? However, if there is some clown sitting in between you and the machine, and this clown can cause delays in the interaction, like a network protocol, for example, then what can go wrong is that you give your money to the machine, and you also press the button, but the clown that is sitting in between delays this message by which the machine decides to refund your money. So what you think here is that I have put the money in the machine, I've also pressed the button, so I now want coffee, right? While the delay has obscured your view of the system. So you expect to receive coffee while the system has not yet received button, so it's free to give the money back to you, and that's something you deem undesired, while the problem is not with the machine, it's with the delay. So how can we solve this problem? There are different ways to solve this problem with asynchrony. One is to require that the implementation is in such a way that is not so sensitive to delays. So if you are writing a code that can decide by itself that I now time out and I don't give you coffee, and you put that behind the network, then you're asking for trouble because according to this model, you should not be able to produce refund if you press button, right? So there is this choice between these two that is determined by the environment, and if the environment can cause delays, then you're asking for trouble if you implement this in such a way, right? Or you can say, if you have such a model, so this is the desired behavior, from that you can detect that this is not a good system to be tested asynchronously, so you should never put it behind a network. Anyway, so the gist of this whole thing is that there are certain types of implementations and certain types of models that can never be tested properly using asynchronous communication. Right? So what we did in this theoretical piece of research, we characterized those semantic conditions that tell you when a particular system can be tested asynchronously and when it cannot be. What we need to do still is to translate this back to a concrete programming language. So suppose you want to test a piece of Java program, how can I make sure by just statically going through the code that this is a proper system even if I interact with it asynchronously, right? So I guess I can skip through the technical details, and I would like to yeah, sure.
It has to do with the relative order of messages. So if the relative order of messages matters, then the asynchronous network may obscure these delays, right? So you may think that you have sent this first and you have sent the other one second, while the network may just let the second one overtake the first one. And then
so the network does not even respect the order.
No, it may not respect the order. So if there is anything about relative order of input and output or relative order of input, then that may be wrong. I mean, of course, depending on the type of network, if you say my network is always FIFO, then you get weaker conditions on the implementation. Right? Good. So that's some other piece of research that we did. And for all of them, I've put the references so you can later look at the papers. So there is this paper last year and this accepted paper in Software and System Model this year that you can inspect the details of the theory. Good. We have done some experiments. I presented only one case study. We did two other case studies with Philips Healthcare about testing and debugging. And the experiments show that this is a promising area of testing. So this does discipline the effort of testing. And in some cases, we observed that it even saves the effort. So even if you include the effort that you spend on modeling, the total effort that you spend on testing will be much less if you use model-based testing for some types of system. And I don't have time to explain a little bit more what type of system currently we can deal with model-based testing. It should not be too wild of a system. So if the interaction is kind of confined, data does not play a huge role in the behavior, then current technology of model-based testing is very suitable, and that can save quite some effort in testing actual systems. So there is this paper that we published last year in the Practice of Model-Based Testing workshop, MoTIP it's called, and there we gathered empirical data of applying model-based testing to practical systems and show that for some type of system it can save a considerable amount of effort in testing. And it can also be very effective in finding faults. We also looked at two theoretical problems, namely decompositional testing that I could not present here due to time, and also the problem of asynchrony and how we can make sure that asynchronous communication does not obscure our view of test cases and the results. We are now working on testing product lines, so how can we factor out test cases for variants of a product line and only focus on differences among these products. Data selection is a very important problem that is not yet properly solved, and we are looking into that. And of course, we want to apply this into practice. So we want to translate what we have found as semantical conditions into some syntactical conditions in terms of a programming language construct. And also, we want to do experiment and measure the size of test cases if you use, for example, the compositional test case generation. And also apply this to actual code and measure the effectiveness of our test cases. Another idea that we have recently started looking at is to combine white box testing with black box testing. So far our test cases look at the system as a black box. Now what if I want to look at more details of the implementation and gather some information about, for example, how data is partitioned in the implementation? This is a very interesting area that has been developed independently various institutes, including Microsoft Research, and they have very powerful tools for white box testing for abstracting the behavior of information using symbolic execution to go through the execution of the actual implementation and also generate concrete test cases using that. And we think it does pay off to combine these ideas of white box testing with the black box view of model-based testing. So thank you very much. That was all I wanted to say, and I would be happy to answer your questions.
Thank you, Mohammed. We have time for some questions. Please, ma'am.
How will the parallelism of the system capture the testing?
Right. I think that was...
Can you repeat the question?
Sure. The question is, how can we deal with concurrency and parallelism in the actual system? So the naive way of doing it would be, suppose you model this font transfer switch as 25 automata, right? What you can do, you can make replication of these 25 automata and compose them in parallel and let the system generate test case from the parallel composition of these models. You see what I mean? So you have a parallel model of the EFT switch in which you have, say, 3 instances running in parallel, and the test cases will naturally take care of the possible interleavings. But, for example, in UPAL, the tool tries to generate the state space for the parallel composition of these 25 automata, and that's a huge monster that it cannot deal with, so the tool will crash. Right? So the way we dealt with it, and I can possibly go back to the slide in which I showed this. So there is no hope that you can test using UPAL-Tron at least considerably concurrent and parallel systems. So what we did in order to compensate for that a little bit, I think I can show it also using this. Yeah. In order to compensate for that, we ran multiple instances of UPAL-Tron in parallel. So we ran, say, 5 different instances of UPAL-Tron, each of which represents an EFT switch, and thereby you get some interleaving of different instances of the test cases. You see what I mean? But
Can you compare the separate traces from each of these?
yeah, the problem is that from each UPAL-Tron you get a separate counterexample, and then you don't know what interleaving led to the actual bug, right? But that's also something that you need to do in the adapter instead of the UPAL-Tron itself, right? Is this clear? But that's the problem with this particular testing tool, because there is no need to generate the state space if you want to do testing, right? That's the advantage of model-based testing in comparison with model checking. In model checking, you try to explore the state space, right? Here, you don't try to explore the state space. You try to take some paths that are more relevant for the actual system, right? So you don't need to compose these state spaces and calculate them beforehand. What you need to do, you need a tool that does this on the fly, so explores the state space while it reaches that particular point, right? Unfortunately, this tool did not support that. And one of the problems that we encountered during this research, and we are now trying to build our own tool, is that the current implementations are rather weak, and they even do not implement the theory properly. So they make some design decisions that are not always consistent with the theory. So what we try to do now is to build something that is at least academically viable. I mean, you can use it for teaching at least, for example, how model-based testing should be done. And we are also talking to people who have done that in practice, and they have a commercial tool in order to also use their tool for practical purpose. But the say, available tools that have been implemented based on this theory either are not supported anymore. So typical examples are Torx and TGV. TGV is a French tool and Torx is a Dutch tool. Or do not implement the theory faithfully. So there are 2 examples. UPAL-Tron does not implement the theory faithfully and also suffers from some other things. And JTorx is another example of a tool that does not implement the theory as it should, right? So we also have a lack of good tools for model-based testing at this moment. Yes?
So, keeping what we can do with model-based testing based on UPAL. What is your
So Upaltron is actually coming from Aalborg. So there was this Greek student of Kim Larsen, I forgot his name. He developed Upaltron as part of his thesis.
Lithuania.
Lithuanian? Okay, I thought his name is Greek. Okay, sorry. The name is a bit complex for me to remember.
Marius Mikuchonis.
Yes, that's the name. So he developed that in Aalborg as part of his master. Yeah, so we used their tool, but this was a kind of small offspring of the whole Upal, say, series of tools, and it doesn't seem to be taken as seriously as the rest of Upal tools. So. Mm-hmm. So I can give you two good examples of model-based testing tools that have been used in practice. One is Microsoft tool called Spec Explorer. It's now included in Visual Studio platform, so you can use that for testing actual .NET applications. It's a rather good tool and it's rather stable, so that's something that you can use. But the theory that is behind it is different from what I presented here. It's slightly different. Another tool is RT Tester tool from University of Bremen, and they have a company behind it, and they actively support it, and they apply it to very big case studies. So these are two examples of good tools that have been implemented, and you can rely on them at least if you want to test a serious system. Right. So I know that Upaltron supports time, at least. To be honest, I don't know of any tool that supports stochastics or priorities on the models. Right, so statistical testing is a separate field that has been rather successful in practical cases. So thereby you can give quantitative guarantees about possibility of finding a fault in the system. So that's a useful thing. I do not know of, say, a line of research, at least in this area, that combines these two together. Right. So usually you do testing in order to establish a certain level of quality. You want to say that it's the probability of finding a bug in this system is this low, right? And statistical testing has been looking at this problem, but I don't know, as I said, of any research, at least in the area of, say, concurrency theory and related notions that combine these two. No, I don't know.
So let me suggest that we take further questions offline, and we thank Mohammed for the seminar.
Thank you.